Hi everyone, welcome back. In this lecture, we're going to go over something that I know many of you like, implementation. So in the previous lecture, we went over proximal policy optimization. As we discussed, proximal policy optimization is a very strong method in reinforcement learning, but it is also applied to language model fine-tuning through RLHF, or so-called reinforcement learning with human feedback. And that's the focus of this mini course. So in this lecture, we're going to go over the implementation details. If you remember, in the previous lecture, we went over all parts of proximal policy optimization. We discussed all the moving parts and the theory behind it. So I recommend that if you haven't studied that lecture, at least go over it quickly, or maybe you can start with this implementation, but then for the parts that you don't get, go back to that lecture to understand the details. Let's start. Okay, let's start with a reminder of what the goal and the setup is. In this case, we have a policy PyTheta, which is a neural network for us, which defines the agent. And this agent will apply actions to an environment. So these actions will change the state of the environment. This will lead into a sequence of actions and states. And there will be some corresponding rewards to any of these actions or some of them. And the goal is that to take a sequence of actions that in expectation will give us very high reward. So the actual goal of training the neural network is that to come up with a neural network that when it observes some state of the system, it can take a chain of actions that in expectation, that chain of actions leads into a very high reward. In this example that we have over here, the agent is defined by a neural network that will change the location of a card, and the card is trying to balance a pole. So the longer it can balance the pole, the more reward we can collect. So the goal in this case is to come up with a neural network that learns after applying some actions to the environment. It will learn after a while how to balance the pole the longest possible. Okay, let's remind ourselves of how PPO works. I think the best way to go over PPO very quickly is to look at the loss terms, because they are the defining factor of how to optimize the policy for a better policy. So we have gone over the detail of these terms here and the rigorous derivation of them in the theory lecture. So this is just a quick reminder. So the first loss term that we have here, the clip pessimistic loss or the policy loss, is the main loss here. And let's focus even only on the first term here, because that tells us the majority of the story. So let's say that we have PyTheta old, which is our current policy, and let's say that we want to improve it through optimization, in this case through maximization. So let's first remind ourselves what the advantage term is. So the advantage term for an action tells us how better or worse that action is in expectation compared to all of the rest of the actions that the policy could take at the state S. So it basically tells us how advantageous that action is. Now, let's assume that we were playing the game with the old policy and we collected the probability of the actions and also the advantages. And let's say that we have currently one action A that we know the advantage for that action is positive. So how do we change the policy in order to get to a better policy? If the advantage of an action is positive at a state, it means that that is a better action compared to the average actions that the policy could take in that state. So meaning that we essentially want to increase its probability to get to a better policy. Now, maximizing this term does exactly that for us. Because look at what we have over here. if the advantage is positive and it's multiplied by this ratio over here, if the probability of the action in the new policy is bigger than the previous policy, the old policy, this ratio will be bigger than 1. A number bigger than 1 is multiplied by a positive number. It means that this is going to increase the value of that number. So essentially it goes upward. And this is compatible with the maximization of this quantity that we have over here. But it works similarly if the advantage is negative. So I will leave the detail to you. But essentially what this term does for us is that by maximizing this term, we are encouraging the policy to take better actions. So going back to all of the terms here, so just a reminder, the rest of the terms here, which is the clip pessimistic loss, basically ensures that that we take actions that are within the trust region. What was the trust region? If you remember, the trust region was a region around the old policy that the advantage is valid within that region. Because remember, if we change the policy too much, we might go to a region that the advantage that we calculated here might not apply anymore. Again, remember, this advantage is not the actual advantage, but it's an estimate, approximation of the true advantage. So this estimation is valid within the trust region. So all of the terms that we have here, just make sure that when we update the policy, we are within the trust region. So the calculation is valid and the policy improves. So that's the main loss here, the policy loss. But what are the other two losses that we have? The second loss, value function loss, is related to the second head of the neural network. Remember, we had two different branches in our neural network, or you could in fact have two different even neural networks. The second branch was trying to estimate how good or bad the current state is in general. And basically that value function estimates the total future rewards for that state. But since we have played the game already through the old policy, we already have a value, a sample value for the future reward of the state S. So v theta is the expected value of the term that we have here in the sigma form. So if we want these two to be close to each other, so essentially the value function to be a better approximation of the samples that we have over here, one of the losses that you can use is the mean square error. That's exactly what we have here. So basically it will give us a better approximation of the expected value of the total future rewards from the state S. There are other variants of the loss here. For example, here we are working with L2 norm. One can work with other norms, L1 norm, L infinity norm, or even other discrete norms. You can also apply clipping mechanism to the value loss here. But the mean square error is a minimalistic loss and it works very well. So I think that that would be good enough for us. Finally, we have the entropy loss. And if you remember, this is related to exploration versus exploitation. So remember, the simplest idea to allow the policy to do a little bit of exploration some of the times is to inject a little bit of probabilistic actions, just some of the actions that are not very likely, but sometimes the policy, we wanted to take those actions as a mean of exploration. And to do that, we just inject a little bit of entropy to the actions. And that's exactly the loss that we have over here, the entropy loss. So the weighted sum of these losses will be the total loss that we have. And by applying the maximization process that I described, essentially we get to better and better policies. And that's essentially how PPO works. Again, remember. Okay, so finally, let's go over the two phases of the PPO. Again, a reminder, we have gone over the details of this in the theory lecture. Just a quick reminder. So it has two phases. In phase one, we work with pi theta old. And what we do is just, we play the game, we collect information. And these information are going to help us to calculate quantities that are interesting to us, for example, advantage, probabilities, and so on and so forth. So after we collect a number of these rollouts or playouts, we go to phase 2. In phase 2, what we want to do is that to work with the PyTheta, this is the new policy, and which is the modified version of PyTheta old, and we want to modify it in the direction that gives us a better policy. We have already gone over the loss terms, so we know that if we optimize for those losses, the policy is going to get better. And that's exactly what we do. We go over k epochs, and for each of the epochs, we take the sample from the rollouts. And for the mini batches, we calculate the loss, and we calculate the gradient of the loss. We apply it to the policy PyTheta to get to a better and better policy. At the end of phase 2, we update the theta old to be equal to the new theta. And that's going to be now our base policy, or PyTheta old. And we will repeat this process again and again. And that is PPO. For the implementation, we're going to go over the problem of Cartpole, which is a simple problem, but the same implementation can be applied to much more complex problems. So if you go to Gymnasium documentation from OpenAI, you will find many other problems. In this case, the problem is balancing a pole using the cart. So the action space in this case, just a reminder, is a discrete space of pushing the cart to the left or to the right. The goal, remember, is to balance the pole. And the observation space or the state space is made out of 4 entries. The position of the cart, which can be from negative 4.8 to 4.8, basically this window that you can observe here. And the cart velocity, that can be any negative or positive number. The pole angle, that can be from negative 24 degrees to 24 degrees. It is measured from the vertical axis. And the pole angular velocity, that can be take any number. So these numbers will define the state or the observation for us, and we are so this is going to be the input to our neural network, and the output for every state is going to be either push to left and push to right, and the neural network should understand how to balance the pole. So that's in a nutshell the description of the problem that we are studying here. Okay, so finally let's go over the actual implementation. This implementation is in the Jupyter Notebook. It's self-contained. It doesn't need anything except for installing the libraries that it needs. You can also run it on a Google Colab. I will leave a link to that too. So you need a bunch of libraries that you can install. I'm running it in Python 3.9, but anything higher than 3.7 should work. There are some references that you might want to study if you get lost or if you don't understand something. Of course, the main reference is the previous lecture that we went over the theory of the implementation, but there are a bunch of other references too, very good references. Some of them are the references that I talked about them also in the theory lecture. So the links are here. Okay, finally, let's go over the implementation. So as common in Python, we start with importing all the libraries that we need. I also set up a random seed so that we can repeat the experiment if we want to. Also, I'm using a CUDA device. Basically, I have a GPU here. In fact, it should be 0 because I have 2 GPUs on this machine. But this problem is simple enough that even with just CPU, you should be able to run it and it will run very quickly. Okay, so this is the hyperparameters of the training. We have talked about all of these hyperparameters in the theory lecture. So for example, the number of parallel trajectories that we are going to study, the length of each of these trajectories, the general advantage estimation, lambda, so on and so forth. These are the hyperparameters. These hyperparameters are tuned for this specific problem, but in my experiment, these are very good starting point for many other problems in RL. So you can always start with this setup and then tune it for the problem in hand. The only hyperparameter that needs a little bit more thinking is the total number of steps. In this case, we'll leave the total number of steps at 1 million steps. Think about it for a second. This time steps, these are actually steps that are in this experiment translate to maybe 1/10 of a second, right? Roughly, because it's not equally distance in the time, but roughly 1/10 of a second. So we need around 100,000 seconds of training for the model to be able to perform very well. Eventually it will converge and it will perform very well, but just compare that with the human performance. So the human probably with just a few minutes of trying to balance a pole, in fact in a much more complex environment of real world, you will be able to do a decent job. But in this setup of RL, we will need to train for much longer. This is a problem that RL is really wrestling with, and this is one of the main problems, in fact, in RL. There has been a few very good papers that I will send a reference here that came out recently to fight this problem called sample efficiency, but it's a very wide open problem. So for the problems in RL, typical problems, usually you need in the order of tens of millions of samples, to some more complex problems might need billions of samples. Of course, for much more complex problems, you might even need trillions of steps for the model to converge. So that's the hyperparameter setup. Let's continue. Okay, the next thing that we want to study is the environment. In fact, I think since it's specific to the Gymnasium library from OpenAI, there's no need to spend a lot of time here. There's some setup that I use for example, how to visualize it and how to save the video out of the performance and so on and so forth. We put a bunch of these environments together to create a parallel environment. So in this case, we have an environment that the number of parallel environments for the total of 32 environments that are running in parallel. And in fact, let me just rerun the experiment all the way to here. Okay. So okay, let's go over the model. Okay, so for the model, remember the model that we have here, which we sometimes call it in the RL setup, the agent, is a neural network. And the neural network that we have here has two heads. One head creates the value function, and the other head is about the policy, basically plays the game. So the setup for the model is like this. I'm a huge fan of minimalist, simple solutions, but whenever you can come up with a better solution without making it much more complex, it's usually a good trade-off. So it's common that for a problem as simple as this to use only just a standard feed-forward neural networks, and I'm pretty much doing that, except that I'm setting up a very good setting here, which is in line with the most advanced setup in the neural networks. In fact, this is kind of a copy of the feed-forward layer of some of the newer language models, that what they do is that they have some embedding layer, and then they project this to a wider embedding space, and then again shrink it back to the same dimensionality of the embedding. And then there is a residual connection that goes from the input to the output. So it is essentially the same thing that we have here. So we have some embedding, we have some layer norm at the beginning to normalize the input. Then I'm using JLU, which is quite similar to ReLU nonlinearity, but it has a smaller saturation area. And I also have a dropout. And as you can see at the very end, I pass the input to the block above it, and then I add it to the original input, which is kind of a shortcut, essentially a residual connection. So let's go over the neural network. The neural network is made out of, the first layer is just an embedding layer. So it gets the observation and then embed that observation to some dimensionality that you specify. Here, I'm going with 64. For this problem, even a smaller embedding layer probably works. For much more complex problems, for example, in language, as we will discuss later, you will have much larger embedding dimensionality, usually for the language in the order of several thousands of dimensions. Then there are the shared layers. These are the layers that are shared between the two heads of the neural network, the policy head and the value head. And finally, the architecture here is just a bunch of these blocks that we defined earlier. And finally, we pass it to the value head in the value function, or we pass it to the policy to get the corresponding values out of it. So for the value function, the output is going to be just a value, and for the policy, the output is going to be the action, basically what action to take, which in this case is going to be a discrete number, either 0 or 1 for left and right, and the probability of the actions that we had in that state, the entropy of those probabilities, and finally the value of that state. Okay, so that's a pretty simple setup that we have here. We call it the agent, which is a neural network, a standard, in fact, neural network from PyTorch. The only thing that here that you might want to think a little bit more is this initialization that we have over here. Basically, rather than just looking at the kind of typical initialization that we have in neural networks, we use an orthogonal initialization. This gives us essentially a very widespread original state for the neural network, because if you remember, at the beginning we want the entropy to be very high. We don't want the model to really focus on one set of actions. We want the model to explore at the beginning for all possible good actions. So that will allow us to do that. Yeah, so that's the setup for our neural network, our agent. One thing that I forgot to mention, in fact, two things. One is related to why do we have shared layers here? So we don't need to. In fact, you can have two separate neural networks, one for value and one for policy. And it's very common to do that. From practical perspective, it's easier to have separate neural networks that you train separately. From theory perspective, if you can merge them, if the tasks that they are creating are somehow related to each other, which in this case is, you are essentially doing multitask learning, which is a preferred method for training a neural network. So that's why we have, in this case, think about it. We want to look at the state of the system and we want to project create a value out of it, which specifies how good or bad the current state is. And the other one is going to create an action. So these two are kind of related to each other through the state. So it makes sense to have several shared layers and basically train those layers through the losses that in this case is going to be multitask learning. But you can also train them separately, then there's nothing wrong with that too. The other thing that I wanted to mention is that you notice that sometimes the policy also accepts actions, and you might be wondering, why do we want the policy? Policy is supposed to create the actions, so why do we allow it to, if we want to give it also the action? So if you remember from the theory lecture, when we are going over the PPO, we have two phases. In phase one, we will go over the game and we play it. We actually take actions. But in phase two, we just analyze the actions that we took and we try to modify those actions to better actions. But we don't actually take actions. So this is for phase two, as we will see later in the implementation too. Okay, next. The next thing that we studied is generalized advantage estimation. Just a reminder of what the advantage is. Advantage calculates how better or worse the return of taking the action A at this state is compared to the expected return of all the actions in that state. Essentially, if you look at this picture, it says what it is. Let's say that you are at the state S and you have different options to take for the action. And the advantage is a rough estimate of the expected value of the return of taking action A, the future reward of taking the action A compared to other trajectories that we might take. Essentially, it says that how better or worse it is the particular action is compared to other actions. And remember that we went over the approximation of this quantity and we came up with a reverse recursive formula that we have over here. If you don't remember that, I recommend that you go back and take a look at that part of the lecture. What we have here is exactly the implementation of generalized advantage estimation. In fact, it's very close to the pseudocode that we had over here. So we get some inputs. The advantage initially is 0 at the terminal state, and we roll it back and we go over the trajectory and we calculate all the advantages based on what we have collected. So note that the only difference between here and the formula that we have over here is the addition of this quantity mask. But this is nothing complicated. The mask essentially says that if we are looking at some of the trajectories that have ended quicker than the maximum trajectory length, then for those portions that are after termination, we don't want to do any calculation. Those are not the steps that we want to consider in our calculation. So we mask those. But the rest is essentially what we have over here. So we have the delta and we have the last advantage that updates the advantages when we go over the sequence in reverse order. So we calculate the generalized advantage estimation, and that gives us the advantages values. These are approximation of the advantages and the returns. Okay, the next step is the phase one, which is rollout storage creation. So remember in the phase one, what we do is that we go over n parallel rollout of the game. Basically, we play the game in n parallel sequences, and then we collect the information along those trajectories. So we collect the logits, we collect the values and the advantages, and then finally we store all these quantities into a storage. So that's phase one, that we actually play the game, or our agent plays the game. So here is the create rollout function that runs parallel trajectories and then creates the rollouts. At first, what I do, I create empty arrays. Well, not exactly empty. These are arrays that are set to 0 with corresponding correct dimensionality, and I put them in the device. It's generally a good practice that when you are dealing with large arrays and you want to store them, you first set aside some portion of the memory for them. So after that, I will go over the rollout, and essentially I apply the policy to the observations, and I create the values, the value, the entropy, the log probability of the actions and the actions, and then I apply those actions to the environment, and then we collect the reward, if any, and also the next observation. So we collect all these values, all these quantities, and we put them into the storage, to the rollout storage. This specific part here is just to keep track of the return along each of the trajectories. So if a trajectory terminates, we look at the total reward of that we collected over that trajectory. So yeah, so that's the rollout creation. But for rollout creation, in addition to the rollout creation, this part is very common in reinforcement learning. I have this extra step that is not common in reinforcement learning, but it's common in natural language processing, in NLP, and because we want to have a smooth transition going from RL to the language domain, it's better to start working with this because it's, as you probably already know, in computer vision or in NLP, it's very common to create a data set, a PyTorch data set, and feed this to a data loader to create your random batches. And that's exactly what I'm doing. I give it the rollout and the advantage and the returns, and it basically put them into the memory of the storage, which in this case is a standard PyTorch dataset, and then I ask for an index and it will return that item from the rollout to me. The only thing that you have to think about is that at this point, rather than having n parallel different trajectories, I flatten them out and I put them next to each other because I already have aligned all of the quantities that I wanted. So there's no need to keep track of the order anymore, and everything is encoded in the index. So I can flatten them out now and work with just simply one index for each of the portion of the data that I want to take a look at. So this is now a data loader. Next, let's take a look at the loss functions. So these are the three losses that we have, and we basically look at the weighted sum of them. So for example, the clip loss, of course, is very important, so it gets the highest weight. So for example, entropy is not as important and we give it a lower weight, and so on and so forth. So we take the weighted average of these losses, and that will be our total loss. So you can see that this formula that we have over here, it's exactly corresponding to the clip loss that we have over here. So the old log probabilities and new log probabilities, and then when you subtract them and take the exponential, remember these are logs, so exponential of a log will give us the ratio exactly as we have here. But if you remember, we discussed that this is more numerically stable, so that's why we do exponential and log rather than just looking at the ratios. And the rest is quite one-on-one correspondence between the formula that we have here and the implementation here. The only difference is that we have a negative sign here because in the standard PyTorch optimization, we want to minimize always. So, but in the RL setup that we wanted to maximize the objective. So nothing complicated. The value loss also very just simple mean square error. Nothing complicated here, and that corresponds exactly to the mean square error that we have over here. So that's the loss function. So this is the training loop. It has two phases. Let's go over the implementation. We first create an agent that is the same neural net that we studied before. I also put it on the device. In this case is a GPU. I create a standard Adam optimizer here with the learning rate that we specified before in the hyperparameters. And then the training loops starts here. I have some quantity that keep track of the returns of different of the playouts of the game, and we have some quantities for to go over the progress of the training. So here is phase one. As you can see, I first play the game and create some rollouts. And then I calculate the advantage and returns of those rollouts. I put them into a storage data set, which is a standard PyTorch dataset format. And then I feed it into a PyTorch data loader so that I can create mini batches of size that I specified in the hyperparameter in a random fashion through the data set. So basically collecting some of the mini batches, random mini batches from the storage. That's phase one. In phase two, I will go over analysis and updating of the model. So I have this scheduling, a learning rate scheduler here that starts from the original learning rate and shrink it linearly to 0. So it's a linear scheduler, if you know what it is. And then the training loop starts here. I have a number of epochs. If you remember, it was like the K epochs that we had in the theory lecture. And then I go over the batches in the train loader. I collect the values that entries that I'm interested in. I give it to the model. This time I do not play the actions. I want to just calculate the probabilities of those values of those actions in my current policy, which is now a new policy. And then I go over the losses. I calculate the total loss, which is the weighted sum of those losses. And then finally, I do the backpropagation. This is the standard PyTorch backpropagation, except that it has this extra term here, which what I do here is that sometimes if the gradient gets very large, I clip it. This is again some common practice that you do to avoid overshoot. Note that RL in general, training RL is a lot more finicky than trainings compared to the training of, for example, a visual model or natural language model. So you usually put these things in place to avoid overshooting or unstable kind of behavior. And finally, I do the optimizer step. And that's it. And I print some of the things for progress. That's the training. And in fact, let me just run everything. While it's being trained, I will talk a little bit about some of the terms that we see. So note that I'm printing the return of the episodes here. And basically, it starts with some play out, and whenever it terminates, it prints some of those terminated games here. And as you can see, it's increasing. It started with something like 20 or something, and it is increasing when we go over the training. Note that it's common in the training of, say, visual models or language models that you print the loss. But if you remember from the theory section of theory lecture, the loss that we have here is only a local approximation of the actual objective that we had. So it's really not that helpful to print the loss. The quantity that you want to keep track of is the return. So you want the model to convert to some good return. Remember, the original goal was to be able to get in expectation very high values of reward, which the total reward is the return value. And something strange happens here. It seems that some of the rewards are maxed out at 500 and it doesn't go higher than that. And it's because of this specific game. In fact, this specific game has a cap of maximum 500 total reward. And that's why when the model gets really good, it essentially learns how to balance the pole, and the pole never falls down. But the maximum reward that you can collect is 500. And you can see that now after some iterations, it almost always hits the 500 mark. Sometimes it makes a mistake. And this is, if you remember, this is exactly the exploration. Sometimes it explores these new actions, and some of the times those new actions are not good actions. But in majority of the cases, now that it knows how to play the game, it plays it very well. So let's wait for it to finish. And in fact, we can just in a few seconds see the result of our work. So this is exciting. Oh, so, yeah, I'm smoothing out some of these values. So if it is smoothed by the exact number that is multiply of the rewards, of the total number of steps, it gives me this error. But let me in fact not really fix that. I'm just gonna add one to it that's gonna fix it. Oh, yeah. Okay, so that was a fun bug to fix, and in fact, I'm not gonna cut it out. So you guys gonna see me struggle with adding a little bit of things and not working. I will leave it to you to figure out why that change didn't work. But sometimes, if the number of returns is the same as I want to smooth out things, right? If the number of steps that we have, the number of returns that we have is divisible by that smoothing factor, then it's gonna lead into division by 0. So not that important. It's not related to this discussion here, and that's why, in fact, I didn't pay that much attention to it before. But anyways, that's fixed. Let's forget about that. What matters here is the progress of the training that we see. So as we discussed, this specific game is maxed out at the value of the total reward of 500. And you can see that it goes up, and this part here, you see that it did some kind of exploration, which was really bad, but fortunately it could recover from it. And it's not always the case. In RL, a lot of the times that if it does some exploration and it leads to bad results, it cannot recover from it. But in a simple game like this, it can. So, and as you can see at the very end, it converges to very good, stable result that most of the time it just collects all of the possible rewards. And let's take a look at the actually a play out of this. So I'm now creating a video of this model that we trained, and let's take a look at the play out in action. So I'm going to play it out so you can see that it does a good job of balancing the pole. And in fact, it collects all the value, all the possible revolves till the end. It never fell down, but the game finished. So one another game that you can just apply this. In fact, you can apply what we implemented here to many other games and many other RL problems. But another game that is a much more challenging game is the game of Breakout. And I left here for you some extra imports and some environment definition that should be modified according to that game. And also some model definition that should be changed according to that game, because we are going to actually use a convolutional layer, because we're going to look at the images of created by that game, and then the RL model, similar to a human, is going to observe those images and try to understand what the correct action is. So, but I'm not going to go over the full implementation. I leave that as an exercise to you. I tell you that most of the things that we created in this implementation remains unchanged. Even the hyperparameters, most of them should remain the same. The only thing that you have to change is that you have to increase the total number of steps significantly by a factor of 30 or 20 to get to good results, because this is a much more complex game and will take several hours, in fact, for the model to converge. But after you get the convergence, you will get some good results. In fact, let me find some good results from before, after we train the model, and show it to you. Okay, so this is the result of the training with the same implementation, but the breakout game. Now, something very interesting that happens here is that, let me maybe go a little bit further ahead. Something very interesting happens here. The model tries to dig in at the two ends so that it sends the ball inside the portion in the middle, and it collects a lot of reward by doing that. And that's quite interesting. You see that it's trying to dig in at the two ends and tries to send the ball inside those holes. And by doing that, it's planning to collect a lot of reward. Of course, as you can see, it's not successful yet, but eventually it will be successful of sending the ball inside, and that collects a lot of reward, as you can see over here. So something interesting that is going on here is that you can see that the model is actually doing planning. To me, planning is very closely related to intelligence. In fact, think about it. The more intelligent a species is, the more planning it can do for the future. And essentially what we see is that we created, in a way, a true artificial intelligence here. Of course, it's not general purpose, it's very specific for this game, but it's very interesting. And this is, to me, it's very different than the type of models that you create, for example, for object detection. They do have some type of reasoning and planning in those models too, but those are very trivial level. Essentially in the form of statistical feature matching. But here, the model is actually doing some planning for the future. And that's very interesting. Okay, good luck. We're done with the implementation. And I see you in the next lecture where we go over the language material. Talk to you soon.